Okay, so we were looking at reactive synthesis in the last lecture. So we looked at LTL synthesis problem and we said that this LTL realizability is indeed 2exp time complete. So uh, uh, and also this theorem says that when an LTL formula is realizable, we can compute a transducer that realizes it. And we also showed some example where there exists an LTL formula for which it's indeed not realizable. Okay, there can exist LTL formulas that are not realizable. And as we said, that the lower bound can be proved using a reduction from alternating EXP space Turing machine. Alternating EXP space is indeed the same as double exponential time, 2exp time. And so this alternation was introduced in this paper called Alternation, which was by Chandra, Kozen, and Stockmayer. Okay, so this is a beautiful paper. And this lower bound, in fact, the lower bound for this reduction, that it's indeed 2x time hard, that this was in Rosner's thesis. And this result also was there in a Popple paper in 1989. This was by Amit Noeli and Rosner. So for the upper bound, we say that you can essentially start from an LTL formula. You can convert this into a GMBW, which can be by the Vardy-Olper construction. So this is exponential in size of the LTL formula. And this can be translated to an NBW. And this is just linear translation, linear blow-up. And from the NBW, you can construct a DPW, deterministic parity word automaton. Okay, and this was a construction which was given by Neil Peterman. So this construction is very similar to Safra's construction. In case of Safra's construction from NBW, construct a deterministic Rabin word automaton, DRW. Here you are constructing a DPW, deterministic parity word automaton. And then we need to solve the parity game. So from this DPW, you can construct the parity game, which we saw. For example, like this was this example of unrealizability we saw earlier, right, in the last class, where it was like uh, we so the formula, so the LTL formula is like the first output should be a 1 if and only if there are finitely many A's in the input. The input alphabet was AB, the output alphabet was 1, 2. So we are talking about synthesizing, uh, synthesizing a circuit. The reactive synthesis problem for such a specification, this is an LTL specification. And we indeed showed that this particular LTL formula, it's unrealizable. So now, yeah, so we had to solve the game there, and we essentially showed that the system player or player 0 does not have a winning strategy in that parity game. Now, so once you have the DPW, you can construct the two-player game from the DPW. So there were states for the environment from which the environment can produce an an input later, and then these are the states of the system, and the system produces an output later, right? So uh, this is the game, and then one needs to solve the parity game. And the parity games, we know that both the players have memoryless winning strategies in the parity game. And I also talked about this algorithm. It's called the Zia-Lonka's algorithm for solving parity games, whose complexity is n raised to d, where n is the number of vertices in the game and d is the number of priorities, or it's the index of the parity automaton, the number of priorities or the index of the automaton. So n raised to d. Now, how do you get then the double exponential complexity upper bound? It's like, so the DPW is already it's double exponential in the size of the LTL formula, right? You get one exponentiation here and another exponent. So this is linear, and then one exponentiation here, right? So, and then also in the DPW, so if you start with, let's say, M is the number of states in the NBW, then the number of priorities or the index of the DPW is on order n. This is the number of indices. Okay, the index or the number of priorities is order n. I call it D. And if like if in the parity game, R is the number of the vertices in the game, and then D is the number of priorities, then it can be solved in R raised to D. And R is essentially it's of the same order as the number of states that you have in the DPW. Okay, so uh, so this is like we have the number of vertices, and the number of priorities is exponential in the size of the LTL formula. Why exponential? Because the NBW, the size of the NBW, the number of priorities is of the same order as the size of the NBW. Okay. So because as I said that if you start with an NBW of size M, then the number of priorities is of order n, right? So if your NBW is already exponential, the number of priorities that you have is exponential. So you get something like this. This is the number of vertices raised to number of priorities, n raised to t, for solving the parity game, right? And this gives you a double exponential upper bound for solving the parity game. We can also have an associated lower bound result, which says that there exists a realizable LTL formula. So essentially, like when you are talking about finding a strategy, right, of the strategy of the system player in order to say that the LTL formula is realizable, right? So this particular theorem says, which we saw last time, is that there indeed exists a family of LTL formulas of size order n square, for which the minimal realizing transducer is of size 2 raised to n, of the order 2 raised to n. So at least 2 raised to n. So every realizing transducer will have a size of order of order 2 raised to n. Sorry, 2 raised to 2 raised to n, double exponential size. Okay. So you have an LTL formula of polynomial size. Okay. And the minimal realizing transducer will have at least double exponential many states, right? So essentially, if you can think of this, we define this language where you had an x after a shard. So this is the crux of the language. So you have like, so this for every n, you can define a language kn, and then somewhere between two shards, you have an x, and then after the dollar, this x has to be matched. Okay, so essentially here, and x is a string, n-length string of zeros and ones. Okay, and now there can be, so this part says there can be multiple such strings, and a DPW, if you think of this, a DPW will try to remember all the different such sets of n-length strings that it has seen so far, and then if it sees an x, it tries to see that if it has already seen this x, right? If it has already seen such an x earlier. So it can see multiple such Boolean strings of length n. And when it sees such an x, it just try after the dollar, if it sees a binary string of, as it sees a binary string of length n, it tries to see if it has already seen this x earlier. Okay, so it needs to remember all the different sets of, I mean, it needs to remember the set of different n length binary strings, right, that it has seen. So if you, and in fact, we saw that this particular such a language can in fact be represented by an LTL formula which is of size order n square. Okay, this can be represented, and now we are talking about like primarily like, so I just tried to give you an intuition of that how the DPW would work. It would remember the set of different n-length strings that it has seen until this part, and then when it sees the x after the dollar, it sees that whether that x has earlier appeared. Okay, so now we would argue that any such transducer, okay, will have at least doubly exponential number of states. Okay, so how to argue this? So consider that you consider these subsets of different strings of length n. Consider different subsets of strings of length n. How many such subsets are possible? How many such subsets are possible? So how many strings of length n are there? 2 power n. Okay, so now you have 2 power 2 power order 2 power 2 power 2 raised to 2 raised to n many subsets of different strings of length n are there. Clear? And suppose S is such a set. S is one such set where you have k many different strings of length n. Okay, S is such a set. Now you can consider a string US which is like sharp y1, sharp y2 up to sharp yk, then followed by a sharp and a dollar. Right? If you recall that after the dollar, you are going to read an x, and all you want to see that if x is one of these yi's, right, then it will be in the language. Now you can think of another set R, another set, let's say R, which is different from S, which is different from capital S, and without loss of generality, you can think of the following, that x belongs to S minus R. Since R is different from X, there exists such a string X of length n, right? A binary string X of length n such that X belongs to S minus R. Now, you see that US dot X, correct? So, if there are, in particular, if there are less than double exponentially many states in the transducer, then there exists, by pigeonhole principle, two such sets R and S, such that R and S are not the same, and by reading a string US and by reading the state UR, by reading the string US and by reading the string UR, you reach the same state of the transducer. Correct? And now you see that US dot X, since X belongs to S minus R, US dot X sharp omega, it belongs to Kn, but UR dot X sharp omega does not belong to Kn, and hence the contradiction. Clear? So every such transducer hence should have at least double exponentially many states.
So there exists an art like this.
Yeah. So again, like, so suppose if you have, so how many such sets are there? How many such sets are there? There are double exponentially many such sets.
So you are proving my contradiction. So for contradiction, let's say there are less than 2 power n many subsets.
Correct.
Then there exists another set R which is not same as S.
No, then there exists a pair of such sets. Right? There exists a pair of such sets. Okay. Let's say S and R. Okay. Yes. So I'm not actually.
Yes, okay.
I'm just saying that S is such a set, but I'm now coming to like I'm not fixing the S.
Yeah.
I'm actually saying that if there are less than double exponent 2 raised to 2 raised to n states, then there is a pair. So suppose S is one such state and then R is another such state in the pair. Right? S is a state and R is a state. These two are the pairs. Right? And such that they are not the same, and in that case, X without loss of generality, X belongs to S minus R. So I also did not say now that what is the formula is like, okay, it accepts this, and whenever it sees the X, it will output an F. Okay, so phi defines this language, the Kn, and it says that whenever this match happens, the transducer will output an O. Otherwise, it's not going to output anything. Okay. So this is the formula. Okay. So all the other letters are in the input set, and this new atomic proposition O belongs to the output set. So the output alphabet only consists of this O, and everything else, all the other letters are in the input alphabet. Okay, so this is That
No, but in a transducer, you have output at every transition.
you have an output, but you may not like the if the output
Empty.
alphabet is empty, then you are not outputting anything. I mean, it's like an empty
Yes, but
epsilon
I'm
or
just trying
epsilon.
to think how the transducer look like in this case. When you have only one element
Right.
O that is printed like at the very end of the of reading the word.
Correct. Not very end, but like when you are uh, reading this hash sharp
Yeah,
after the X.
after the X.
After
If
the X, you are reading the sharp, and then you will say you output the
if it matches.
if it matches. Yeah.
So it basically does not output anything till it.
You are not outputting anything until you reach this sharp. When you reach the sharp, then you output the O.
Sure.
Okay.
Hmm.
And the state should remember that what are the different different n-length strings that you have seen, the set of all the n-length strings. And then it tries to see if X is already, it has seen that.
Okay.
If X appeared in that set.
Yes.
But this is like an upper bound thing. We are talking about how the transducer would ideally look like.
Yeah.
But here we are trying to prove actually no transducer would be there which will have less than double exponential many states. Okay, good. And then we looked at these omega regular games, which are essentially like these are games. And then there is a winning condition, which is given by an omega regular automaton, right? So let's say this can be given by a DPW, for example. And uh, so this may be like a parity condition which can be given by a DPW, and we define something called a composition game. So what is the idea of the composition game? Then you have this game and this winning condition which is given by the DPW. I'm taking a product or taking the composition of this D and the game graph G. Okay, so this now I get a new game, a larger game where the state space is Q cross V, and this is partitioned into like the vertices of the two players, which are like Q cross V0 and Q cross V1, and the set of edges there is E prime, and I have a priority function which I called omega prime, right? So earlier I had V0, V1 are the in the original game. This was the partition, and then E was the set of edges, and here in the DPW I have a priority function which is omega. Okay, and now uh, in this game, like so I am putting the priorities on the vertices in this composition game, which is like omega prime qv equal to omega of q, right? So this is the thing. And then I have an edge from qv to q prime v prime. If first of all q prime equal to delta of q comma v. So from q you are reading v and you are going to q prime. So note that in this DPW, the alphabet is the set of vertices of the game graph, right? So the game graph has the set of vertices V, and this DPW is reading those vertices. Correct? DPW is reading the vertices, and this winning condition is on the sequence of vertices that you see in the parity winning condition, right? And so you have QV comma Q prime V prime belonging to E prime, right? In this composed game. If V comma V prime, if in the original game V comma V prime is there in the original game. Huh? And then from Q, if you read V, you go to Q prime. So this is in the DPW. So this is in the DPW and this is in the game G, right? And this is how we are constructing, right? And so essentially, intuitively, you can think of this that the composed game DOG proceeds in the same way as G, but it uses the DPWD as a memory, right? It keeps track of the DPWD. It uses that DPWD, the states of that, as a memory in the composed game. So that's the idea. Now one can say that this is not very difficult to see that player I, any player 0 or player 1, player 0 is the system player, player 1 is the environment player. Player I wins from a vertex Q comma V in the composition game if and only if player I wins from vertex V in the original game G. Okay. Now, we just looked at this for player 0. And what was the idea? That in fact, like suppose you have a player zero has a winning strategy in the composition game, right? And you can think of like, so what was happening in the composition game? So you have, suppose something like you had QV, and from QV you could have like, suppose there were in the original game you had V to V prime and V to V double prime. Maybe these were the vertices, these were the two edges. Now, if you had delta of q comma v equal to q prime, then in the composite game you will go from qv to q prime v prime and q prime v double prime. Okay. On the other hand, suppose you were in a state q1v and delta of q1v is q double prime. Then from q1v you will go to q double prime v prime and q double prime v double prime, like that, right? Now, if you have a strategy in the composition game, now it can say, the strategy may say that when I'm in QV, I'll take this transition. Whereas when I'm in Q1V, I might take this transition, right? So that means that in the original game, I might sometimes take this transition and sometimes I'll take this transition, depending on what which state the DPW is in. So in the original game, I can get a strategy from the strategy of the composition game by using the state space of the DPW as a memory. So I'm using this as an auxiliary memory and I can construct a strategy for the original game from the composition game. Now, what about so this is for player 0, and similarly, you can also do it for player 1. Okay. But now, what about the other direction? How do you prove it for the other direction? That if I have a strategy in the original game, then I can also get a strategy for the composition game. How do you do that?
We assume determinacy.
If you can use determinacy, then it's just trivial, right? So you can just say that now, suppose now we prove this for I equal to player I equal to 0. Now you say that okay, for player I equal to 1 also it's a very similar proof. Now I use that for I equal to 1 in this proof. Okay. So suppose player I wins in the composition game. That implies player 1 wins in composition game implies player 1 wins in the original game. This is by the previous direction. So this means player 1 by contraposition, right? Player 1 loses in G implies player 1 loses in the composition game. It means by determinacy player 0 wins in G implies player 0 wins in the composition. Okay, correct? So this is the idea. We saw this. And now you see that omega regular languages, this winning condition can be given in terms of a DPW and you need a finite memory, right? So this theorem says that if you have a game like this and the win is where the win is an omega regular objective, then the winning regions for the two players denoted by win 0 and win 1, they are computable and both players have finite memory strategies because this win is a omega regular condition, right? And it can be expressed using a DPW. Okay. So you have, as I said, that the memory is essentially given by the states of it's a function of the states of the DPW. So you have finite memory strategy. Clear? Okay. So corresponding to every omega regular winning condition, I can construct an automata with finite number of omega regular automaton with a finite number of states. Correct. So that's the thing. Okay. Now, when we are doing the composition, I also mentioned that it is also essential to have this thing called like a deterministic automata. When we are doing the synthesis, you are doing the composition, it's important to have a deterministic automaton, and a non-deterministic automaton may not work. Why? Because it may be possible that indeed the formula is realizable. So that means that when you are constructing the game, so we looked at like how do we solve the synthesis problem? Again, let's try to recall. We have the LTL formula. From this, we constructed a DPW, which is double exponential in size. And from the DPW, we constructed the game where we had two kinds of states. Some states belong to player 0 and some states belong to player 1 or the environment. So the environment states are the one from which the environment gives the and then I have like if the environment state chooses an input I from a state Q, then I go to a system state Q comma I, from which the system will choose which output to select, right? Choose the output. So we saw such a thing. So indeed here this is like your this is the DPW, and this is an environment state where it gives the input. Okay, and so here the input alphabet is P and the output alphabet is just Q, and the system has to, and this is a system state, and the system has to decide what output to choose. And we saw something like the following, that initially, because of this non-determinism, even though this automaton is going to accept such an LTL formula, and indeed one can also show that it's not very difficult to see that this formula is realizable. So when at the next step, if the input is P, then you output Q. That's the thing. Next of P equivalent to Q. At the next step, you produce the input is a P by the environment, the output produced by the system is a Q, right? So this is, I think, not difficult to see that this is indeed realizable, right? I mean, you can construct such a DBW instead of an NBW. This is an NBW, but one can, if you construct a DBW and construct the game out of the DBW, then you can see that the system player has a winning strategy. On the other hand, because of the NBW, what happens that initially, right? So what is the language like? So you can choose initially anything. Then if there is a P, there is also an associated Q. If there is nothing here, right? So this is the empty thing. If there is nothing here from the input side, then on the output side also there is nothing, right? It's like next P if and only if Q. So either both PQ have to be there or none of them is there, right? So now what can happen is like if the system produces, let's say, the environment produces a P, then you can go there, and then for example, like whatever be my output, okay, so I can then, I mean, with this P, I can choose some output, doesn't really matter, right? So I can choose some output. I can, suppose I go here, now you see that the system player can produce an empty input, and for with this empty input, whatever be the output that I produce, I am going to kind of lose the system player. So whatever is the output, whatever is the input that the environment produces, the system is going to lose because it's not going to be able to match. Okay. On the other hand, like, so the main thing that we saw is like if you come here, then you should accept with the PQ. If you come here, then you should accept with the empty set. And the system player is not initially able to distinguish like or resolve the non-determinism initially, that whether it should go to the I mean whether it should take like I mean go to the B or it should go to like C, this relation. So initially it is not able to like resolve the non-determinism. Okay, so though
Okay, so these are okay. I thought this is one big game. Okay,
sorry,
no, this is like the tree of that game, right? The right hand side is the
no, so this is the automaton and this is the
okay, no, I
corresponding
thought-
game.
Okay, it's very close together, so I thought it's one big automaton. Okay.
No, this is the automaton. The automaton is on the left side, the game is constructed on the right side. And it's essentially because of the non-determinism that the system player is not able to resolve, right? So for example, like, so the point is here, like if I, suppose I reach B, okay, suppose the system player reaches B, then it's like now the environment from this state can produce a null input. If the environment produces a null input, then the system player cannot win from this state. Here, if the environment produces a P, then the system player cannot win, right? But if you had merged these two states, Okay. And then you know that if you have something like this, that on PQ, I will go here, on empty also I will go here, which is exactly like this, what this DBW does. Then corresponding to any, if now the environment produces a P, the system will produce a Q. If the environment produces nothing, then the system will also produce nothing.
I was just confused because they was very close together, so I thought that
Yeah.
arrow into with square is stronger.
Right.
Okay.
Okay. Yeah. No, I think, sorry.
So
It's I think this is a different
sorry.
thing. It's like
Oh,
this.
okay, it's clear.
Okay, good. Thanks. Okay. So I hope this is clear. Okay, so now we will move to today. We will start these games on graphs where the thing is that you can think of that this is like this composition game where the winning condition doesn't come separately, but it is inbuilt in the game graph, in the arena. Okay, so you have like the winning condition, it is given as a sequence of like a set of sequence of vertices, like set of different paths. Okay, so that defines the winning condition. So it's essentially like the win is a subset of v omega. And more specifically, we can say if you can consider a game graph, this is like the sequences actually correspond to paths in the game graph. Okay, paths in the game graph, and a path is a sequence of vertices, right? And so, and the game graph essentially looks like you have such as there is an arena, you have player one and player one vertices, player two vertices, some player one vertices. So again, it's partitioned into V0 and V1 corresponding to the vertices of player 0 and player 1. Okay. So the winning condition, it is embedded inside the arena. Okay. And we are going to look at particularly these things, reachability, safety, Büchi, coBüchi. And we'll also say briefly about the parity game. Okay, and all these games, these 5 games we are talking about, they all have memory based determinacy. Okay, now now just a few definitions. A play in an arena is an infinite sequence such that, like infinite sequence, which is this row 0, row 1, etc., belonging to this v omega, such that the consecutive vertices that form an edge for every such. So all the consecutive vertices, they come from an edge, right? So that is a play, and a game is said to be determined if this the winning region for player 0. So a winning region is essentially the set of vertices from which it's a so a vertex V belongs to the winning region of player 0 if the game starts from V, and player 0 can ensure that no matter how player 1 or the environment plays, the resultant play, it has a strategy such that the resultant play is in this winning condition. Okay, is in the winning condition. Okay, so it will become clearer in a while when we look at the examples. And so the winning region of player 0 and the winning region of player 1, uh, if you take their union, it essentially is a set of all vertices. So from every vertex, either player 0 wins or player 1 wins. So every vertex belongs to either the winning region of player 0 or to the winning region of player 1. Okay. And if a game is determined and from every vertex V in win I for some player I, if it is the case that player I has a positional strategy from this vertex V, then the game is positionally determined. Okay, so both the players have positional determinacy, essentially memoryless winning strategies. Then the game is said to be positionally determined. Okay, if one of the players has positional determinacy, it's called a half positional determinacy. Good. So let's start with any question on the definitions. No, right? Okay, so now let's start with these games on the first objective, which is called the reachability objective. In the reachability objective, we consider let's say R to be a subset of vertices in this arena. And the reachability condition, it is a set of all the plays, set of all the different plays, such that there exists some vertex in the place, set of all such plays row, such that there exists some vertex in row which reaches the set R, right? This occurrence of row is the set of all vertices which occur in the play row. Okay, so reach R is the set of all such plays that reach the set R. Clear? So this is the thing. So there should exist some row I, some I, such that row I belongs to R. Clear? So this is the reachability objective or reachability condition. Here is an example. Like, so suppose the reachability set is V4 and V5. And now I claim that both the players have memoryless winning strategies here. Okay. So for example, like if you are in, let's say, if you are trying to construct a memoryless winning strategy for player 0 of the system player, see, look at all the vertices which belong to player 0 and define what the strategy should be. So let's say from V1, you can directly go there. Okay. From V8, you can directly go there. From V7, you can come here. And then, like we already saw that from V8, you can go there. And from V1, you can come here. So suppose, let's say this is this is what is the strategy of player 0. Okay. Now, let's try to see from which of the vertices player 0, if the game starts from that vertex, player 0 has a winning strategy. Okay. So suppose the game starts from here, then this is already in this set R, right? So this is winning for player 0. This is winning for player 0 because if the game starts from here, it's already in this set R. Similarly for V5 also, right? What about V6? If the game starts from here, then player 1 has only one choice. It has to come to V7. Then player 0 can move it to V8, and then from V8 it can move to V5. So this is also, V6 is also in the winning region of player 0. Okay. On the other hand, if the game starts from V0, then player 1 can move to V1, and suppose the strategy of player 0 was to come here, then the game is restricted to here and can never reach V4 or V5. Now suppose instead player 0 wanted to send the token to V2. Okay, then V2 from here, player 1 can again send it back, and then the game will be here. And even if the player 0 after a while wants to send it here, player 1 can again send it here. So the game is always restricted to this set of vertices. Okay, right? So that's the thing. Now, so these vertices are actually winning for player 1. Okay. Now, if I have to define the strategy of player 1, then I have to define the strategy of player 1 for all the vertices that player 1 owns, right? So, for example, from V6, it has only one choice, going to V7. From V5, it can either go to here, or it can come to here, right? So suppose it goes to here. Okay, it doesn't really matter, like it goes here to V7. Similarly, from V6, we already said it goes to V7. From V4, let's say it goes to V8. So that is the strategy we have defined. From V0, it goes to V1, and
Why
from
are
V.
we defining strategies for squares here?
We are just defining the strategies for the other player also. We are saying that both the players here have memoryless strategies. We are defining the strategy for the system player as well as we are defining the strategy separately for the other player.
Oh.
Okay.
So ideally, we would only define strategies of the system player in system's winning region and the square strategy in the
For the square winning region. So what is the objective of the square player here? The square player wants to, or the player 1 wants to ensure that the system player cannot reach this set R. right? So that is the objective. So from these vertices, indeed, player 0 cannot ensure that the game will reach here. So how does the game again is played? Like you start from you put a token in a vertex V, and then whoever wins, suppose V is owned by player 0, so V will send the token to one of its adjacent vertices. Then suppose it sends the token to a vertex V prime, and V prime is owned by, let's say, player 1. Then it will be player 1's choice to send the token to one of the adjacent vertices. Okay. So we saw such examples earlier we have seen. Okay. Now, how do you solve this reachability game? How do you solve the reachability game? So we use something called the controlled predecessor operator. Okay. So let's say the controlled CP, I denote it by CP of a set U, okay, it's essentially the set of vertices belonging to, so I is the player I. It's a set of vertices belonging to the player I's vertices, right? Such that it has some neighbor which is in the set U. Okay. And for the other player, all its neighbors should be inside U. So for example, like here, I consider, let's say, if I say that CP 0 of R, CP 0 of R, where R is V4, V5. So what is this? What is the CP 0 of R? What is CP 0 of R?
V3,
V3,
V8,
V3,
V8,
V8.
V3 will be there and V8 will be there. Okay. Now this particular which belongs to player 1, it has one neighbor which is here, which is in V5, but there is another one which goes there. But when we are considering CP of 0, for player 1, all the vertices should reach R, right? Which is not the case. So we will not include V2 here. In fact, CP of 0 has V3 and V8. Okay, like this. Now, I'm defining something called the attractor of player 0. Okay, so attractor of player I. Okay, so initially I define attractor of player I with the superscript 0 for the set R. Attractor of player I with the superscript 0 for the set R, which is the same as R to start with, right? And in the n plus 1 iteration, sorry, I say that this is like attractor, I'm computing this iteratively, like attractor I n of R union the CP of I of this attractor I with the I n of R, right? And you do keep doing this computation until you reach a fixed point. And so you can compute this way, attractor of player 0, attractor of player 1, right? So let's look at an example. So initially, my R is V4, V5. So I say my attractor, let's say player 0 of R is R. Now attractor 0, 1R is attractor 0 with a superscript 0R. So recall that this is the player 0, and this is the iteration until you reach a fixed point. Okay, so now union CP of 0 attractor 0, 0 of R. So what is this? This was R union, we saw V3, V8. Okay, so this gives us V4 or V3, V4, V5, V8. Okay, so next I'll do attractor 0, 2 of R, which is this set attractor 0, 1, R union C pre 0 of attractor 0, 1, R. Okay. So now what is this? So we need to get this. So this we already know, which is this. What is this? CP of 0 of what this? V3, V4, V5, V8. So we are V3, let's say V3, V4, V5, V8. So this will have V7 also, right? So now this will have V3, V4, V5, V7, V8. Okay. And after that, if we compute again attractor 0 of 3R, we will get everything from there, and we are also going to get V6. Right? And then we'll see that this stabilizes. After that, it doesn't change. Attractor 04 equal to attractor 03R. Okay. Okay. So now I'll say that this is the entire attractor of player 0 where it stabilizes. Okay. So this is the winning region of player 0. And the winning region, so this is equal to the winning region of player 0. So what does, suppose if I say attractor 0j of R, what does it mean? What does it mean to say attractor 0j of R? What is this set?
If all vertices from which player 0
Zero
can reach
can
are in
reach.
at most.
In at most j steps, right? Set of all vertices from which player 0 can ensure, right, that no matter how player 1 plays, it can reach R in at most j states. Clear? Okay. So this is called the attractor of player 0, and similarly attractor of player 1. Okay, so this is now we have defined this, and now the this is the winning region for player 0. I'm sometimes writing as W win, sometimes writing as W, but yeah, okay. So they're the same thing, winning region, and and the winning region of player 1 is essentially the complement of that set. Okay, so this is how we solve the reachability games, and reachability games are determined, and positional winning strategies suffice, and it can be solved in time, which is linear in the number of edges in the underlying elements. If you solve this algorithm, this iterative algorithm, it's a linear time algorithm, and the strategies for both the players, player 0 and player 1, you can have positional strategies. So how will the strategy look like? So if there is a vertex of player 0, so I'm trying to define a player 0 strategy, which is in attractor 0 I plus 1. So the strategy sigma of V will be some V prime, where V prime belongs to attractor 0 I. Okay, the previously computed set, in the previous iteration, the set that you compute, right? That is the thing. Clear? And if you are already in, let's say, if you are already, so this is for V not in R. If V is in R, then sigma V equal to V prime for arbitrary V. Because you have then already won the reachability objective. You don't need to, you can go anywhere, right? For V, if V belongs to R, then it can be anything arbitrary, right? Okay. So now we talk about safety games. So what are safety games? Now you have a set of vertices, like, so these are, so these are my set of vertices, and you want to restrict the game always in this set of vertices. You would never allow the token to go to either V0 or V6, right? So this is what player 0's objective is. Now the safety game can be looked at as a dual of the reachability objective. Why so? Why so?
If a player wants to stick to the safe region, that means the other player wants to reach the.
Yeah. So if player 0 wants to stick to this region, then the objective of player 1 is the opposite. So which means player 1 would like to reach either here or here. So this is a reachability game for player 1, right? So if we understand that, then uh, essentially we can say that for the safety objective also, both the players have memoryless winning strategies, right? Here player 0 is trying to stay, sorry, I was stay in this part. Yeah, this is what I think. Okay, so player 0 would like to stay in this part. So just formally defining what is the safety objective is the set of all plays such that the set of states occurring in such a play is included in the safety objective if all the states that are occurring in this play, they are in this safety set S, right? So S is a subset of V, and you always want the set of states visited by a winning play to be restricted to this capital S, this set of vertices. Okay. So this is what we define. Player 1 here tries to reach outside the safe set, that is to V minus S. So it's a reachability objective for player 1 with the reachability set V minus S. Clear? Okay.
How do we come up with a strategy for safety?
So
like I can see the strategy for player 1 in this game.
correct.
But we see.
Yeah. So you have a strategy for player 1, and now I have to get, so I got the winning region for player 0, right? And so essentially, the player 0 would choose anything from here which would keep it inside this set. That's all. Good question, right? So player 0 would choose any outgoing A which will keep the game inside the set S. Right? So a strategy, winning strategy for player 0 is to keep the game W0. Yeah, you are right. In the winning region. Okay, yeah, you are indeed right. Okay, so it's like sigma of V.
Winning zero has to be a subset of this.
No, but you can't just take any vertex.
So
any
sigma
and
V
takes you to another vertex.
equals V prime
Yeah, no.
You need to stay in the winning region.
belonging to W0 if V belongs to W. If V belongs to W0. Okay. Equal to some, otherwise some arbitrary. Otherwise arbitrary V prime. Okay, so this is a strategy for player 0. Good. Sorry. Okay, thanks. Now we talk about Büchi game. So what is the idea of a Büchi game? So essentially you have again a set of vertices, right, which is a subset of the whole set of vertices. So I call this as F. So you have a, I call this the recurrence set. So this set F, and the idea is that Büchi F, it's a set of plays such that it would see some vertex from, I mean, a winning play is one which will see some vertices from F infinitely often. Okay, some vertices from F will be visited infinitely often. So that is inf. So it's like the set of plays rho such that inf of rho. What is inf of rho? It's like the set of states which are visited infinitely often, intersection F should be non-empty. So that means there exists some state from F which is visited infinitely often in the play row. Okay, so then this is a winning play. So then the Büchi objective consists of such plays. Okay, now how do we compute the Büchi? How do we solve the Büchi game? So essentially, the winning region. How do we compute the winning region for the Büchi objective? So the idea is the following. So suppose you have such a set, it's a V, and then you have the B here, right? You have the B. Okay. So you'd like to, so suppose you start from some vertex here. Maybe it is possible that you can reach here once, and maybe you can, let's say, come back, and then you reach here again, and then maybe you reach here for the third time. But after that, you go back, go here, and then you cannot come back. Okay, you are staying here. Then certainly I would not want to keep this initial vertex from which the game started in the Büchi winning region for player 0, because you can visit this set B only finitely many times, right? Only maybe sorry, okay, I said F, right? Okay, yes. So I would see the F only finitely many times. Okay, now one thing to note is that suppose there is a vertex. Suppose there is a vertex from which player 0 can never reach F. Player 0 can never reach F. Now this vertex B, so V does not belong to attractor 0 of F. Now clearly V is winning for player 1 because you cannot even visit F once, right? Okay. And also you can think of like uh, the uh, the set of vertices, from which, let's say, player 1, can ensure that it can reach such a vertex. Okay. So if in addition, suppose you have V belongs, suppose there is a W which belongs to attractor 1 of such a vertex V. Okay. Then W also does not belong to wing 0, or I can say W belongs to wing 1. Clear? So I'm saying that if there is a vertex V from which player 0 cannot ensure that it can reach F, then it, of course, even once, then it is of course winning for player 1, vertex V. And now if it happens that this, on the other hand, player 1, there is some W from which player 1 can ensure reaching the vertex V, then W also belongs to the winning region of player 1. Because if the token reaches W, then player 1 can send it to V, and then V is winning for player 1 again, because player 0 cannot take the token to F, right? Okay. So let's now look at the algorithm in a bit more formally with this intuition that we have. So we compute the Büchi winning set for player 0 and player 1. We do this iteratively. I mean, more specifically, we'll see that we are trying to increase the player 1 winning set, and then when it stabilizes, this iteration will end. Okay, we'll stop the iteration, and then what we will have is like we are going to have the W1, which is the winning region of player 1, and we'll say that V minus W1 is essentially W0. So this is how we are going to, first we are going to compute this W1. Okay, so that's the idea. So let's see how we are going to do that. So initially we have F. we have the f, which we say f0. So this is the iteration, like you have an I for the ith iteration, and you compute from which vertices you can send the token to f or f0, right? Or fi in the ith iteration. As player 0 can send it to the fi. Okay, player 0 can send it to fi. Okay, or to start with can send it to f, just to keep it simple. From which vertices player 0 can send it to f. Now this vertex v is something, let's say it cannot send player. I mean, I was trying to say that if you cannot send, then clearly this is winning for player 1, right? So now I say you have attractor 0 of f, attractor 0 of f. So whatever doesn't belong to the attractor 0 of f, that belongs to player 1. Okay, that belongs to player 1. And now I am also seeing, I mean, it may be possible that, see, this some vertex, like, okay, some, oops. So I just want to remove this thing. It may be possible that, see, there may be something here, something which is here, it belongs to attractor. So something which is already in f, it belongs to attractor 0 of f. This is clear? Something which is in f is a subset of attractor 0 of f, right? Now, there may be a vertex here, from which player 0 cannot bring the token here, right? Which is like, this is v minus attractor 0 of phi. So there will be like this vertex from which player 0 cannot send it, correct? Now, there may be a possibility that there is a token which is, sorry, there is a vertex here inside the f, and player 1 can send it to such a v, right? So in which case, this reaching here, reaching here even for player 0 is not good, because then player 1 can send it outside, and then player 0 cannot send the token back. Okay, so I am computing now what is the attractor 1 of this W1I. What is W1I again? The set of vertices from which player 0 cannot force the token to this f, right? And I'm seeing like what are the vertices inside f, okay, such that player 1 can force the token. There may be some vertices here inside f from which player 1 can send the token to this attractor, to this set, right, which is the complement of the attractor of player 0, right? And then I'm going to remove such vertices from my set f, right? Because even if player 0 again sometime later from somewhere comes here, player 1 will send the token here from which player 0 again cannot come back. So seeing these vertices is not good, because I want to see the region f infinitely often, because the set of vertices f infinitely often. So I have this W1I, and I compute what is the attractor 1 of W1I, and I remove these vertices from my fi, and I get fi plus 1. Okay, and I iterate this until my W1I and the fi, they will stabilize. So what is happening is here, like my fi is reducing, and if my fi reduces, then the attractor 0 to fi will also reduce. Hence, its complement will increase, right? So the wi is increasing monotonically, right? Or it's monotonically non-decreasing. At some point of time, say after the mth iteration, it will stabilize, and my f is gradually reducing, right? So this is what is the idea of the Büchi game. So let's look at an example. So here you have f0 equal to f. Let's say this is v4 and v6. And now what are the different vertices from which player 0 can ensure that it can reach v4 and v6 to start with. So I'm computing the attractor 0 of f0. So what is that attractor 0 of F0? I can reach V4 and V6 from V3. Is there anything else?
V7.
V7, yes, V7. And of course, we have the V4 and V6, right? We also have this by definition. V4, V6, V7. Okay. Now, what are then V minus attractor of 0 of this thing? So that gives me V0, V1, V2, V5, V8. Clear? So these are the ones which are here. Now, I would like to see, so this is already winning for player 1. This part is already, these vertices are already winning for player 1. There will be more vertices which are winning for player 1. Now, I'm going to remove from my F0 all those vertices from which player 1 can take the game to these vertices. So essentially, I'm looking at player 1 attractor of these vertices and removing them from the F. So what are the player 1 attractor of for this set, right? I can clearly from V4 I can reach V0, right? So hence player 1 attractor of this set includes V4. So now I'm from the set F0, I'm going to remove V4 also. Hence F1 is going to be V6. Clear? And I repeat now. Now player 0 will consider attractor 0 of V6. What is attractor 0 of V6? You have V3 and V7, right? And hence W1 becomes
The gray one.
sorry,
The gray portion.
yeah, so we have now V3, V7, V6. So these two are, so V4 is gone now. Okay. So now I have, then if I remove this, so I have this entire thing, correct? This pink, this side. V0, V1, V2, V4, V5, V8. Okay. And now I again do the attractor 1 of W11, but now I see that from here, like from here I can come here, from here I can come here, from here you can only go there. So indeed, the attractor 1 of W11, it has, what does it have? Attractor 1 of, I mean, it is the empty set, correct? Attractor 1 of this set is the empty set. Player 1 from any of the other vertices, no, I'm sorry, attractor 1 of W11 is not adding anything else. It's just W11 itself, right? It's just the W11 itself, correct? W11 itself. And now F2 is F1 minus this, and F2 remains V6 only. So it stabilizes here. And hence W11, this W set also stabilizes. And this is what is the winning region for player 1. And the winning region for player 0 is going to be the complement of that, which is essentially this. Clear? Okay. So this is how I solve the Büchi game. Okay. So W1G is this W1 over all the iterations n that you get there. It just over after some time it will stop, it will stabilize, and W0G is the complement. Now, can you say how many iterations I may need at most? Like this thing, I already say it here. So these iterations, like how many eyes I may need at most? Number of vertices, because huh?
In F.
In
F.
Or what is it in F? Yes, sir.
in F.
Because every iteration you are removing at least one vertex from F.
Yes, right. I'm removing one vertex from F.
Okay.
Yeah. So indeed, this is true that the number of if I don't remove something from F, then I'll stabilize. You are right, absolutely. So indeed, this is upper bounded by the number of vertices that you have in F. Okay. So and all we are doing are some attractor computation. Then the whole thing, this whole algorithm, like in every iteration, we are doing some attractor computation. So and attractor computation, like one attractor computation is linear time. So this is entirely like polynomial time, like some quadratic time we can solve the Büchi game. Okay, so this is, I think, clear. Thanks. I was earlier thinking that, okay, I mean, I thought of a simpler upper bound, which is just the number of vertices. Yeah, but you are right. Like I can indeed like have the upper bound, which is the number of vertices. Good. Um, and here also you can see that both players have optimal memoryless strategies. Now, if I talk about the player zero strategy, what is player zero strategy? If it is in the attractor, so FM was the last that F set that we got, right? It was getting smaller, and FM is the last set that we had. And if V belongs to the attractor 0 of FM minus FM, right? Then it is that attractor. So if it is outside, right? So you have the winning region. You have already computed the winning region for player 0. And you know that if I visit FM, then I'm fine, because from FM, player 1 cannot evict me and send me to a place from which I cannot visit FM again, right? That FM is where it's stabilized. It's essentially that F2. After m iterations, in general, I was saying that this is the FM equal to m plus 1. So this is like the good set. So if I'm in FM, I know that I can again come back to F, right? So this is a good thing. So if right? So Fn is a subset of F, but there can be some other vertices in the winning region, right? So W0, correct? So Fn is a subset of W0, but there can be other vertices outside Fm, which is in the attractor 0 of Fm, right? There can be attractor 0 of Fm, which is also in W0, correct? Okay. So isn't it equal? That's what you are asking. Yeah, it will be. Okay. So now all I'm saying is that if there is a vertex V which is in attractor 0 of Fm minus Fm, sorry, I should write that here, minus Fm, then what will be the strategy of player 0?
Just reach it.
You reach Fm. That is the policy. Okay. And if you are already in Fm, then you would like to go somewhere which is in attractor 0 of Fm. Clear? Okay. Then is it okay? If you are already in Fm, if V belongs to Fm, then you try to stay in attractor 0 of Fm. Anywhere. You go to anywhere in attractor 0 of Fm. You can again come back to Fm, right? And if you are outside Fm but in the attractor 0 of Fm, then you would like to reach Fm, because there is an attractor strategy, which is a memoryless strategy, right? So that is the thing. And for anything else, you can do anything arbitrary. So this, and if you are here, like if you are outside Fm but in attractor of Fm, player 0 attractor of Fm, then you play the attractor strategy, which is a memoryless strategy. Clear? We saw that, right? Okay. And if you are already in Fm, then you stay within the winning region somewhere. Clear?
So this second line. So this is also memoryless.
This is also memoryless.
You can always choose the same successor.
You can always choose the same successor.
Yeah. You can always choose the same successor. Okay, good. Thanks. Okay, otherwise you choose something arbitrary. Büchi games are again determined, and they have positional winning strategies for both the players. And again, as we saw, they can be solved in polynomial time in the size of the arena. here is an example, just another example. Okay. So what is my F set? To start with V2, V4, V6. Okay. Now, what is attractor 0 of F? So how are we going to compute? So you compute the attractor 0 of F, right? So this is what you will do. First, you will compute the attractor 0 of F, and then whatever is not there in attractor 0 of F, so V minus attractor 0 of F, this is winning for player 1, right? And then I see that if there is something in F, there is something in F which from which player 1 can send the game to here, like player 1 attractor. Then I considered the player 1 attractor of this set. Clear? This is what we were computing, correct? And removed this again from F. F equal to F minus this set. This is what we are doing, right? So let's do this on this game. So initially so this is my F, right? From which vertices player 0 cannot take the game to F? What is not in attractor 0 of F? Like, so first of all, what is attractor 0 of F? What is attractor 0 of F?
Yeah, V1 to V6.
V1 to V6, V3, V4, V5, V6. Then what is this? V minus attractor 0 of F is V7,
Yes.
right?
Yes.
So now we have to see from which vertices
Attractor
player 1 can take the game to
that is
V7.
V6.
That is V6. Exactly.
V6, V7.
So attractor 1 of V minus attractor 0 of F, which is equal to attractor 1 of V7. This is V6, V7. Clear?
Mm.
Now I'm going to then remove V6 from my F. So my new F, F1
V2.
equal to then becomes V2, V4 or V2, V4, V6 minus V6, V7. So this is equal to V2, V4. Clear? And then next time what happens? So this is my F. My F is now V2, V4. And what are the vertices from which I cannot come here?
Normally can come.
V4, V5, V6.
This entire V5, V6, V7, right? It's not there in the player 0 attractor of V2, V4. So these ones, okay? And now I compute the player 1 attractor to this set, which is also include V4 now, right? So this is the player 1. And now I remove this from F1, which is V2, V4. And I am only now left with V2, which will be my F2. So I get F2 equal to V2. Okay, and I continue this, and what shall I end up with? So what is the player 0 winning region here? Empty set. So in fact, here we get finally that W1 equal to V and W0 equal to the empty set. So indeed, if you see that I cannot from anywhere visit this region, this Büchi, this recurrent set infinitely many times. From anywhere I cannot visit this recurrent set infinitely many times. So indeed we computed that W0 is the empty set. Clear? Now,
So does it mean that if I have F2, then player 0 can reach some vertex in F at most 2 times?
I is the set of vertices that player 0 can ensure reaching
At least.
at least
So can I
yeah, at least I times.
So V2 will be in F2 but not in F3. So it means exactly.
Okay, you're right. Thanks. At least I times. Yeah. And now if you look at the strategy of player one here, that is also a memoryless strategy because all that it does is again the attractor computation. Like the thing that it will be using in its strategy is the attractor computation to those like uh, stays. I mean, it's the attractor computation to these vertices. Okay, and staying in those vertices. So essentially, like player zero, wherever from the set of vertices, this set of vertices, like v minus this thing, which is winning for player one, right? This is also a sub game in which player one would win and keep the token there itself. Okay, okay. It's a trap, so we call it a trap for player zero. I did not define it, but it's a trap for player zero. Okay, so essentially it means this is a sub game. So the definition is it's a sub game from which player zero is player zero by itself cannot come out unless player one sends the token outside this set, outside this subgame. Okay, right? And so player one can keep the token there itself by again using a memoryless strategy. Just so it's for player one also, it's a memoryless strategy everywhere. Like you have the either the attractor or you keep the subgame there. And that subgame is winning for player one because it's not in the attractor strategy for player zero to reach that F, right? So good. Now, what about coBüchi games? coBüchi games are dual of Büchi games. Okay. So here you have a coBüchi set, or it's also called, yeah, I mean it's a set C, which you would want to visit only finitely many times. Okay. From some point on, player zero wants the game to be restricted to the complement of C. Right? So here this has some row is winning. If it is like the set of vertices which are being visited infinitely often in row, it is restricted to V minus C. Okay, it's a generalization of safety game where the unsafe vertices, in some sense, like the C vertices, can be seen only finitely many times. Right now, it's a dual of the Büchi game in the sense like what happens is now if you consider that player zero at some maybe player zero starts from here and would like the game to be restricted to here. Maybe it may come back here for a finitely many times, but then after a while it will just be staying there, right? So that is player zero's objective. So what is player one's objective here? So what is the objective that player one would want? So player zero would like to restrict the game after a while in this part. Clear? In this part. Like it may start from here, it may come back to this C for a finitely many times, but after a while, the game will be restricted in this V minus C. That is player zero's objective. What is then player one's objective? Player one being
To visit C.
to visit C infinitely often. Like it comes, it comes, it comes, it comes, like to visit C infinitely often. Then player zero, if that is the play, then the play will never be forever will be in V minus C. Right? So player one's objective is to see C to visit capital C, this set infinitely often. Right? Hence, it's a Büchi objective for player one with the recurrence set C. So it's a Büchi C for player one. Clear? So again, thus coBüchi, both the players have infinite memory strategies in the coBüchi game. Optimal strategies, optimal memoryless strategies, and the coBüchi game can also be solved in polynomial time in the size of the arena by solving the Büchi game with respect to C. Clear? Now, all these games we saw so far, they can be solved in polynomial time. Now, in the parity game, you have like a priority function which puts a priority on each of the vertices. So it's puts a priority which is a natural number on each of the vertices. So the parity condition is like this. So I say that in a play, the play is winning. You look at all the vertices which are occurring infinitely often and see the maximum of the priorities, the max priority. And I'm saying if the max priority is even, then it is a winning play. Okay, this is how the parity condition is defined. It doesn't really matter, as we saw earlier, like the max or mean or even or odd doesn't really matter. So this is how the parity condition is defined. And we know, again, I mean, we are not going to do this in this lecture or in this course, that in fact memoryless optimal strategies also exist for both players in parity games. Okay, we saw this earlier, but yeah, we are not going to do this. And it's also known that parity games can be solved in time NP intersection co-NP, and no polynomial time algorithm is known. In fact, there was this paper in 2017 which found a quasi-polynomial time algorithm for parity games, which was in stock. It received a best paper award. And so any question here until this thing, like these are just some remarks that I made. We are not going to see how parity games are solved. I already mentioned about the Zielonka's algorithm. So this is one algorithm to solve parity games. And there are more recent algorithms. It's a very active area of research and how to solve parity games more efficiently, right? And there are games which use memory also, like these games on graphs, exactly these games. I mean, it's not that the winning conditions are separately given in terms of like an automaton, as we saw in the composition games. Even on the games on graphs, there can be like there can be games which have like which require memory. For example, look at this street game. Okay, so here there are three vertices. So recall the street objective. So what is it? It says that if you have some k such pairs in the street game, and alpha 1 beta 1 alpha 2 beta 2 alpha k beta k such pairs, it says that if alpha I for all I if alpha I is visited infinitely often, then beta I also has to be visited infinitely often. Now here in this game, everything belongs to player 0, all the vertices, and the condition is v comma q v comma r. What does it denote, this condition? Capital V, so the set of all vertices.
If you visit V infinitely often, then you visit Q infinitely often. And if you visit V infinitely often, then you visit R infinitely often.
So what does it boil down to?
Visit Q infinitely often, and you visit R infinitely often.
You visit Q infinitely often and R infinitely often, because V anyway will be visiting infinitely often in any place, right? So you visit Q infinitely often and R infinitely often, right? So thus a play is winning for player 0 if and only if it visits Q and R infinitely often. Now you see that there is no memoryless winning strategy here for the split condition. Either you play this if for memoryless, then you will be producing this play, which is PR omega, or you do this if it's a memoryless winning strategy from this, then you do PQ omega, correct? In order to visit both Q and R, I mean, you have to take this edge infinitely often, also take this edge infinitely often, right? One possibility is that you use a 1-bit memory and you just alternate, right? And then it's a winning strategy for the split game. Clear? When it comes from here, you go here. When then it comes back, then you go here. Okay. So you can in fact use a Mealy machine to represent such a strategy. A simple Mealy machine with two states, correct? Like you have a, so we talked about what a Mealy machine is, what a Moore machine is. So you can use a milli machine encoding the strategy. How will the milli machine look like? You can start from here, and if it starts, so suppose initially suppose the token is here. Okay, so you see a P, this is my initial state. You say I will go to the right initially. So I go here, R. Okay, then when I see R, when I see R, I'll go to P. I'll go to P. And then when I see P, I'll say I'll go to Q. Sorry, I'll go to Q, this one. I'll say I'll go to Q, right? And then when I see Q, I'll say I'll go to P. Like this. When I see again P, I go to R, right? So this is what this milli machine is doing. Clear? Okay, clear? So you need a milli machine with two states. Okay, good. So I'll just make some quick remarks now, maybe another 10 minutes I'll just take, and about some other things which we are not going to talk about in detail in this course. So we looked at Markov chains and we looked at PCTL, probabilistic computational tree logic. We also looked at, in the context of model checking Markov chains with respect to PCTL specifications, PCTL properties. Okay. Now, a Markov decision process. So when we talk about reactive synthesis, so Markov decision processes are relevant. Okay. In the case of model checking, we talk about Markov chains with against the PCTL properties. Here we have Markov decision processes. In Markov decision processes, you have essentially like instead of a single distribution, so this is a Markov chain. You have a distribution with probability 0.5, you go to this state, with probability 0.5, you go here. In an MDP, you have multiple distributions from a state. So you can, with probability, so there's a blue distribution and there's a green distribution. So the blue distribution as here, like with 0.5, you go to S1, with 0.5 probability, you go to S3. The green distribution says with probability 1, you go to S5. Okay. And the strategy in an MDP can be either you choose the blue distribution, or it can be another strategy which chooses the green distribution, or it can be a mix of the two strategies. You can say with probability 0.5, I will choose this distribution, and with probability 0.5, I will choose this distribution. If you do that, then you will essentially get a Markov chain with probability 0.25 here, 0.25 here, and with probability 0.5 here. Okay, that will be a Markov chain because you are choosing these things with probability 0.5 of these distributions, right? And one important thing in an MDP is something called an end component, which is like it's a subset again of the set of states, such that for all, so R is an end component. If for all the states P in R and all actions A, such that there is some action from the state P. So this action is there. Action is nothing but a distribution, the blue distribution or the green distribution, which we call the action. An action is a distribution. Such that if this action is available from the state P, then we have either all the transitions on action A, they go out of R, or they are entirely within R. So for example, like if you have some states like this, so the blue ones form, sorry, these ones.
Also need strongly connected.
Yeah. And yeah. And yeah, you are right. And so number one, so there are two conditions. Thank you. So R is strongly connected. Okay, so this is strongly connected, and you also need this. So for example, if it happens that there is a something like it goes here, then goes here, and maybe it's like this. There is some such action here, then there is some such actions going here, But then you see that from here, let's say with probability 0.5, I am coming here. And with probability 0.5, I am coming here. Then this, though it is strongly connected, it is not an end component. So this is not an end component, right? On the other hand, these two states form an end component because you are entirely here, right? The actions that you have, they are entirely here. But suppose now you have another action here, right? So these are all with probability 1. So then this 4 is an end component. You could have again another state also, which is like, let's say, which is of this form, in a good color, which is of this form, and you are staying, let's say, you are here, okay, and then like this. These things still make an end component because for all the actions, this forms an end component because like for all the actions, either this is the case that post P a intersection of R. So this is my R. Indeed, for if you take this, so intersection, this is empty, like taking this, the successor that you get, there is no intersection, it's not in R. Or it's the case that for all the states here, like if you take the actions, you end up reaching the states which are within R, right? So indeed, this is an end component, and this is also strongly connected, right? A maximal end component is a maximal end component in the sense that one in which there is no end component you will get by removing some state from there. So that is a maximal end component.
By adding. You cannot extend them.
Yeah. Sorry. So it's a maximal end component. I cannot add another state in order to get and I still get an end component. Yeah. Okay. So if R is maximal, then there doesn't exist end component R prime, where R prime is a strict superset of R. Okay, yeah, thanks. Okay. So as I said, like if you now, if you consider an MDP and if you select a strategy, you end up getting a Markov chain, right? So what are the difference? So here, for example, like you choose the action A with probability 0.5 and action B with probability 0.5, and you get this Markov chain, right? So all these transitions have now probability 1/4. Okay. We looked at probabilistic computational tree logic. I'll just skip this. We'll also looked at the semantics of PCTL with respect to Markov chains. And so in general, strategies can be of different forms. So a strategy is essentially given a finite history. You look at the distribution over the set of possible actions. Okay, that is a strategy. One can also look at deterministic strategies. So a strategy maps finite paths to distribution over actions. One can also look at deterministic strategy, which chooses one action among the set of available actions. And a memoryless strategy is one which is independent of the past, but only depends on the current state, right? And there can be 4 such combinations, which is history dependent or with memory and then randomized, like you have the distribution. Another is history dependent deterministic. One can talk about memoryless randomized and memoryless deterministic. Any question? Right? So you have 4 such combinations. Now, if you look at the synthesis problem for PCTL object, so what is that? Given a PCTL formula and an MDP M, you ask the question, does there exist a strategy such that the resultant Markov chain satisfies the PCTL objective or not? Clear? So, again, given a PCTL formula and an MDP M, does there exist a strategy such that the resultant Markov chain satisfies the property phi or not? This problem is known to be highly undecidable, right? Even for the existing of the history deterministic strategies. Okay, this is highly undecidable. This was a leaks paper in 2006, where essentially it was shown that the synthesis problem for PCTL objective for MDPs, it's undecidable, highly undecidable. If you ask the satisfiability problem, what is the satisfiability problem? You are given a PCTL formula phi, and you are not given any Markov chain. You are just asking the question, does there exist a Markov chain which satisfies phi? This was open for a long time, and it was 2024 leaks, I think. It was shown that this is also undecidable in leaks 2024. It was shown that this is also undecidable. The model checking problem is, on the other hand, we have seen, like, which is you are given a Markov chain and you are given a PCTL formula. You ask the question that does the Markov chain name satisfies the PCTL formula phi? And this is decidable in p time, polynomial time, for unbounded PCTL properties. And if there are these until L formulas, this kind of thing, so it's a bounded until, then then this is in poly of m times n max. N max is the maximal step bound that you have in the formula times the size of the formula. It's this order poly in the size of the polynomial, in the size of the Markov chain, and it's n max, which is the maximal step bound, and size of the formula. Okay, it's order of these three things. So this is the last thing I will mention. So far we talked about finite memory strategies. Finite memory strategies, right? In the reactive synthesis, LTL synthesis, we talked about finite memory strategies. Now, this is an example by a paper by from a paper by Rafael Bartho and Mikhail Rando and Jean-François Rasca, where they are considering such strategies, which is a sure parity and an almost sure parity. So we discussed what is sure condition, what is an almost sure condition. And here there are two priority functions. There are two priority functions. I'm sorry. One is omega 1 and another is omega 2. So each vertex, so each function is of the form this, returing. Okay, two such priority functions. So you have four such vertices. And for example, in this vertex, omega 1 assigns a priority of 1, omega 2 assigns a priority of 0. Here, omega 1 assigns a priority of 2, and here, omega 2 assigns a priority of 1, and so on, right? You can see the priority functions. And all the other actions here, wherever the probabilities are not mentioned, they have probability 1, right? So they have probability 1, essentially. 1, 1, 1, here 1. So only these two, here you have probability 0.5 each. Okay. Now, what you want, what is the objective? You want sure priority P1. So you want to surely, so my definition here is maximum priority seen infinitely often is even. Seen infinitely often is even. Clear? So this is what I want. And how do you think what can be a policy here? What is a policy? I'm starting from, let's say, this thing. And I would have to see, like, surely, for sure, I would like to see on the first dimension, I would always like to see an even priority. And on the second dimension, with probability 1, I would like to see a maximum even priority. On the first dimension, surely, always I would like to see the maximum priority that is occurring infinitely often, that should be even. On the second dimension, with probability 1, almost surely I would like to see that the maximum priority that is occurring infinitely often is given.
Could you label the states?
Yes, I'll label the states. S1, S2, S3, S4.
S2, S3 are only one actions. And S4 also. So strategy is only for S4.
Strategy is only to be defined for S1. Right? Only to be defined for S1. Now, you see that if you try this action, what can happen is like you cannot surely satisfy the first priority condition. If you only try, if you have a strategy like this, right? Because it will come and there is a path like this, which is S1, S2 omega, which is S1, S2 omega, correct? And this path, the maximum priority that you are going to see on this path is 1. So it doesn't satisfy the sure priority condition, right? S1, S2 omega does not satisfy surely P1. Clear? Does not satisfy surely P1. Okay. Or just for the sake of clarity, I'll say maybe I'll use, because I'm using the S, I'll use something else. So what is a good notation? R1,
Okay.
R1, R2, R3, R4 there. So I'll say R1, R2 omega does not satisfy sure priority P1.
So it's possible.
No, so from R1
If you use the R4 infinitely often, then you have
infinitely often.
Okay.
So you visit R4 and then
After a point, you have to stop visiting R4.
Because if you see, the problem is that if you visit on the other hand R4, then the second priority you are not going to satisfy.
yes, so you alternate.
Suppose you alternate.
Yes.
Okay, you go once there
Yes.
and then you come back here. You are alternating,
P2 is max order.
right? So if you are alternating, then what happens? Like sometimes you may come here, sometimes. So when you will win? It is like if you see this, if you see this vertex, infinitely often with probability 1, right? Then you are going to satisfy the almost sure P2 with probability 1. Then you are going to satisfy, right? If you are alternating, then what happens? With probability 0.5, you may see here, and with probability 0.5, you may come here. Okay. And then you come here, then you are losing the almost sure P2 thing. You are losing the almost sure because you are going there.
So then maybe it's that like you visit, if you visit once, then you go there. Then next time you visit twice, then you go there. If you visit twice, then you go there.
Yes. So in fact, you can show, suppose you have a finite, you want to do this only finitely many times, you would like to take this and then you come back here. Suppose you do this. Suppose you take this some I times.
Yeah, then you will lose on the sure one.
Then
you will lose on the P.
No, I am saying that you do this I times and then you come back. So you take this I times, like do these, maybe you come here. Okay. You take this I times and then your strategy is to come back.
Yeah, then you will lose on
Here.
the second.
So the strategy is to take this, like you take a maximum of I times. If you visit this, well and good, and then you can continue. But if you do not visit this in I times, then you go here, right? So if you do this I times, then the probability that within I times I'm not going here is 1 minus 2 raised to minus I.
It's strictly less than 0.
Which is strictly greater than 0, right? And so there is a positive probability of not visiting this one, and you are not satisfying the sure P1, right? Because you are here, and then you would like to visit this. And then what can happen is that, like, you are doing this again and again, like you are restricted to I times, and then there's a positive probability that with which you are not satisfying your parity condition, right? And then if you switch, then of course you will satisfy here the parity condition. But now if you are doing this, you will satisfy the parity condition by switching the sure parity condition P1. But what about this condition? Like you do this and come back. And then again you are trying this some I times, fixed I times, and then again you are going there. If you are doing this, so there is a positive probability with which you are moving there, moving to the right side, right? Like what I'm saying, that if you do this I times and then just fix I times, so your memory is I amount of memory you are having, right? You need to memorize this I, the number I, that I'll do this I times and then come here. Then, though I'm satisfying the sure parity condition, I will sort of sacrifice on the almost sure part, because there is a finite probability, there's a positive probability that every time I will come back here, and the fact that I will visit this infinitely often is 1. With I'll be visiting this infinitely often, that probability is 1. And this is the maximum priority, which is odd. Hence, with probability 0, I'm going to satisfy the second priority condition, right? If I have a finite memory. Now, I think this is what you were saying, that I'll visit this the first I some once. If I'm here, then I will continue this. Then do it twice. If I see this, then I continue this. If I don't see this in the ith round, right? If I don't see this in the ith round after trying this I many times, then I go back here. And in fact, if you do this, you can show that with probability 1, eventually you will always stay in this region. Eventually will always stay in this region, eventually with probability 1. And in any round, if you actually do not see this vertex, then you will do this. But the probability of doing this in that case will be 0. So, in fact, surely will satisfy the priority, the first priority, and almost surely will satisfy the second priority. But this will require infinite amount of memory. Infinite memory is required. Okay, it's written here. Infinite memory strategy. I'm just writing here. Okay. Okay, so this is the thing, and there are some references. I took this from a talk which happened here at TIFR by Bharat, and then there are some lecture notes from which I took the figures, Zimmerman and Klein and Wienert, these figures that we saw, and then there are some lecture notes by Shaul Almaguer on reactive synthesis, that part. There were some examples which I had from there. So overall, so this is where the course ends. So overall, we had 3 parts in this course. Like, so one was, we started with the omega automata, right? So we looked at Büchi and coBüchi, parity conditions, Radin, and all the other closure properties, various complexity results for the decision problems. And then we looked at the LTL, CTL model checking. So that was the verification part. And at the end, we looked at these games, the infinite games, right? And for these different omega regular conditions, we looked at LTL synthesis, right? And we looked also at LTL, that unrealizability. Like, there are formulas which are unrealizable, right? Even if these LTL formulas exist, it doesn't necessarily mean that all LTL formulas can be realized. And if something depends on the output, depends on what comes as input in the future, you may not be able to realize that thing. And then finally, we looked at these games on graphs. We also looked at the composition games. And we said that if the winning condition is omega regular, then finite amount of memory suffices. And then we looked at omega regular games, right? Games on graphs with omega regular objectives, in particular reachability, Büchi, so reachability, safety, Büchi, coBüchi. and we also saw that for street objective, you need some memory there. And we also just briefly mentioned about Markov decision processes. And this final example we saw, it's a Markov decision process with such kind of conjunction of parity objectives, one sure parity, one almost sure parity, where even finite memory strategies also don't suffice. You need infinite amount of memory. Okay, so any question before we end? Any final question about the course, uh, about today's lecture? Okay, so I'll stop